Okay, so let's look at this example. How is this different from the previous one we worked? One thing you should see right away. Right, the load is discontinuous, which means this applied load, although while continuous over the first 12 feet, changes from 12 to 20. So this means we're going to have to write two sets of equations. One set will be valid between 0 and 12, and the other set will be valid from 12 to 20. Okay? Now, when those two equations meet, when they match at the common point, x equal 12, they should usually produce similar results. So you have a way of checking them. So how do you want to solve this problem? Let's talk about first, I'm going to cut it in this section somewhere between 0 and 12. You want to work the left side or the right side? I think the left side would be reasonable. Now the disadvantage of the left side is I got to find my reactions. So let's do that first. So I'll draw a free body diagram of the right side. I have this load 20 kips. I have a distributed load with an intensity of 4 kips per foot. See, that's 12 feet, and this little section is additional 8 feet. Again, on the left-hand side, I'm going to assume a positive shear force and a positive bending moment. And then I'm going to calculate my concentrated equivalent force. So what would be the concentrated equivalent force for this? Yes, the area under the curve, it's a rectangle, so it's just base times height. So that should be 4 times 12 or 48 kips. And then the distance from the left edge to the centroid for a rectangle is half the distance. Half of 12 is 6. So that should be enough to get started. So now when I sum my moments about point A, I have my reaction moment, which when my sign convention is negative. The 48 kip force creates positive or negative moment about A. Negative with my sign convention. So that'll be negative 48 times a moment arm of 6. And then the 20 kip force out here creates positive or negative. Negative again, right? So that's 20 kips times 20 feet. So we should be able to solve for the moment. I think it's negative. I don't know what this is. This is 400. What is that?
288.
What is it?
It's 288.
Two?
No. 48 times 6.
688. Anybody get that?
Yeah.
Okay, so 688 kip feet. And then if I sum my forces in the y direction, assuming up is positive, I have the shear force acting up. My equivalent force is down, so that's minus 48. And this applied force over here is down. So that looks like the shear is going to be 68 and positive. So positive shear force, negative bending moment at A. Okay? So now, let's come back and look at a free body diagram. And this is going to be valid from 0 to 12. Okay? So I'm going to cut this structure somewhere in here, a distance x away. But it'll only be good from 0 to 12, because after 12 you can see the load changes. So let's draw that free body diagram. So I'll have my structure at some distance x. I have my shear force, 68 kips, and I have my bending moment, which is 688 kip feet. And then I have my uniform distributed load, and it has a intensity of 4 kips per foot. And then I have my positive shear force and positive bending moment at the cut. So far so good, right? I'm going to handle this distributed load by using the concentrated equivalent. So what would that be? Let me write over here on the side. I'm kind of running out of room. So I'm going to say, what is that force? Well, it's a rectangle, so it's just base times height. The height is 4, the base is x. And the distance here, I'll call it d. D is half the distance, or x over 2. So again, this is not a very attractive looking free body diagram, but it has all the components that I need. So if you were to produce this on the exam for this particular range, I'd say you've got more than half the problem done. You're in pretty good shape. So as I mentioned before, now it's just time to kind of crank the wheel. So let's come over here and sum our moments at the cut. Make sure we're in equilibrium. So starting here, this internal moment with my sign convention is positive. This force F, is it creating positive or negative moment about the cut? Positive. So the force is 4x, and its moment arm is x over 2. Then I have the 68 kip force, positive or negative moment? Negative. So that would be 68 times the moment arm of x. And then finally I get the moment here at the fixed end. And with this sign convention, that moment is positive or negative? It's 50-50. Positive. Are you positive about that? Sorry, that was a bad joke. There we go. So therefore, my moment equation, did I get everything? Moment, force, reaction, moment. Yeah. So my moment equation should be, looks like negative 2x squared, that's this term, plus 68x minus 688. And all those would have the units of kip feet. I'll put a line under it so we can see it. Does it work? Well, for this particular problem, I know the moment at this end, right? It's negative 688. So when I put in x equals 0, 0, 0, I get negative 688. Unfortunately, not like the previous problem, I don't have any place to check it to yet. I don't know the moment anywhere else. And when I get out here to 12, though, I can check the moment at 12 to the moment at 12, x equals 12, from the other equation when I get it. So I'll be able to check later. Right now, that's all I've got. So if we continue this, let's sum the forces in the y direction. That should give us our shear force. So the shear force is acting down. Our load F is acting down, minus 4x. And 68 is acting up. So now our shear force should be equal to minus 4x plus 68, and that should be kips. So I can make a couple of quick checks. I know that the moment at x equals 0 should be minus 688 kip feet, and of course my equation gives me that, right? I know that my shear at x equal 0 should be 68. And you can see when you put in x equals 0, I do get 68. And if you take the derivative of the moment with respect to x, do you get the shear? You do. So feel pretty good about this so far, that these might be the equations. But don't forget, these are only valid from 0 to 12. So we have to do this problem again from 12 to 20. So I've kind of run out of paper here, so let me slide this up a little bit. I can do this to start with. So let's make a new free body diagram. So this will be a free body diagram from 12 to 20. So let me cheat a little bit and slide this up here like that. And let's talk about a cut out here somewhere from 12 to 20. Now, do you want to work the left side or the right side? I think the right side would be a much better choice. So let's do that. So I'm going to draw my free body diagram. I'm going to look at just this chunk on the right side. And there's my 20 kip force. Now, that cut from the left edge is still at some distance x. Right? And at that x cut, I have positive shear force and positive bending moment. So what is the distance or the length of my little section? Yeah, the whole distance is 20. So this should be 20 minus x. Everybody see that? Looks a little odd, but that's not a hard structure to work on. So again, right-hand rule, we're going to sum moments at this new cut surface and make sure they're in equilibrium. So let's do the moment here. What kind of moment is this with my sign convention? That's a negative moment. And the 20 kip force creates what kind of moment about the cut? Also negative. So the force is 20 kips. And what's the moment arm? This distance? 20 minus x. So the moment, as a function of x, is simply just minus 20 times 20 minus x. And that will be kip feet. So you don't have to do anything else. That's fine. It's an equation. You don't have to expand it if you don't like. We'll come back to that in a second. Let's go ahead and do the shear force. So I'll assume up is positive, and summing force is in the y direction. What do I have? Shear force is acting up. 20 kips is acting down. That's not much of an equation. The equation for shear is simply equal to 20. So it looks like over these last 8 feet, the shear is constant. All right, let's make some checks. The first one we'll do quickly is the derivative of the moment equal to the shear. If I take the derivative of this with respect to x, what do I get? I get 20. Everybody see that? So that's good. Okay, great. What else do I know about this particular situation? This is a free end, right? What's the moment at a free end? If there's not an applied moment there. 0. So I should be able to come over here and say, is the moment at x equal 20 equal to 0? Well, you plug in x equal to 20, what do you get? 0. So that matches. Okay? Now one more we can do. I can now take the moment from my first equation, which I'll call 1, at x equal 12, and it should be equal to the moment from my second equation at x equal 12. Okay? So if you look back to our first equation, I'll slide it in here temporarily. This guy, somebody evaluate this at x equal 12. And then somebody else, hopefully working together, evaluate this at x equal 12. Well, this is easy. This is just this is a negative 160. So from my second equation, I get negative 160 feet. Hopefully you'll get the same value from the first equation. Just take a little longer. So this equation evaluated at x equal 12 gives you
Negative 160.
Mr. Providence says negative 160. That's great. That's a lot of confidence. That's a lot of checks that seem to work out. So I feel pretty good right now that I could describe the shear and moment variation of this structure from 0 to 12 using these two equations, and then from 12 to 20 using these two. Okay? Any other questions before we stop this? All right, great.